Hello, everybody. This is the seminar series of the Task Force on monitoring the IUFRO Task Force on monitoring global tree mortality and the International Tree Mortality Network. I welcome everyone, and it's actually amazing what we have experienced during the last days. We announced this very late, and within very few days, we had received more than 500 registrations, and this is what we're waiting for everyone to enter the room. Nonetheless, we start introducing the speaker first, Matt Hansen, and I will do a little more of an introduction later on. And then we have from the IUFRO, I think your communication officers, Janice, right? Janice Burns, from IUFRO helping us here with the setup of the seminar. Cornelius Senf, core team member of the Tree Mortality Network. Adriani, also core team member, and Nadine also. Okay, with this, I think I'm going to share my screen to make the introduction. Okay, maybe I should mention first that you will see buttons at the bottom of your screen, which will be important. So you see a Q&A button, which will be useful to you to ask questions as Matt is giving his presentation later on. And there's also a chat button that you can use to forward messages to us. So before we starting the seminar series, I just want to say quickly a few words about who we actually are and how this came to life. For many of us, this is how it started. This was Craig Allen's publication in 2009 showing tree mortality and forest decline from heat and drought, basically on all forested biomes. And then we had many questions how this could happen and whether these events are actually representative for what's going on the globe as a whole, or on all forests of our globe. In 2014, I organized a workshop in Jena at the Max Planck Institute for Biogeochemistry, where we were thinking about the mechanisms and drivers of mortality. We had a very nice attendance, also 60 participants from 18 different countries. We were discussing, as I said, the mechanisms and drivers, but in the end, the main message that came out that global trends of tree mortality remain highly uncertain. This is why we then organized in a much nicer setting than the MPI building in the Hanover Castle, Herrenhausen Castle, a second workshop where we were looking into the trends and causes of global tree mortality. We had here more than 80 participants from 20 countries and covering 6 continents. And after 3 days of very constructive discussions, we came to the conclusion that we need sort of like a permanent interdisciplinary initiative for monitoring, attribution, and forecasting of tree mortality. So this was our next step. And then a few of us came together. We see here Bernhard Schuld on the right-hand side, then Nadine, you've seen it before, Aster, Adriane, and also me, and a former member, Tanya Sanders. We installed, applied, and also got accepted as a IUFRO task force on monitoring global tree mortality patterns and trends. As sort of an extension of this, we decided to also found the Tree Mortality Network, which allows also non-IUFRO members to join our initiative. So this was where Cornelius and Rupert Seidel and also Tom Pugh entered our initiative. And as you can see, by now we have a very nice geographical representation of our membership on that map. And we also, and this was one big advantage of having this mortality network as an initiative of the IUFRO task force, we also have a very highly competitive, scientifically renowned advisory board on which Matt Hansen also is a member. And this is why he is good and invited to give this presentation today. So the idea behind these initiatives is that we have an international interdisciplinary assessment of tree mortality where we join different disciplines, remote sensing, forest inventory, modeling, and ecophysiology. We're trying to quantify mortality trends, identify the causes, and derive long-term trends and patterns. We aim at data integration, so joining different data sources, whether it's from remote sensing, this is what Matt is going to show us today, but also ground-based data, so basically forest inventory plots that we're trying to combine in a common database and make it publicly available. We want to do a causality analysis once we have more information on mortality events out there, so we actually get to the mechanisms that can then be used in modeling in order to improve forecasting capacities of global dynamic vegetation models. So we started a global data integration, doing an online survey that we have carried out this year, this summer, where we had 115 respondents from 51 countries entering information on more than 300,000 plots. This is the first step. We're going to organize a series of workshops in the beginning of next year, where we actually want to analyze that information that was collected and trying to figure out a way how we can combine and harmonize these different data sources in order to extract information that is relevant for tree mortality. All data contributors will be contacted and encouraged to participate. Obviously, this aims also at publications. And the data survey is still open. Here you see the link, but it's going to be distributed via our chat also during this seminar. So general, and this is basically then I'm closing up with this, general information on the seminar series. We're going to plan this at a regular interval between 6 to 8 weeks. If you have suggestions on topics or something that you want to present, please contact us. See the email, treemortnet@gmail.com. Usually what we're aiming for, and this is what's going to happen today, a presentation by the speaker, 45 minutes, followed by 30 minutes of question and answers. And during that presentation, you can send questions relevant to that presentations via the Q&A function. And if your questions are not selected, we apologize, but likely there's going to be way too many. And here it is, our first speaker, Matt Hansen from the University of Maryland. He has done a bachelor's in electrical engineering, followed by a Master of Arts in the Department of Geography in North Carolina, a Master's of Engineering, and then a PhD. And he is a professor at the University of Maryland since 2004. And he is presenting now global forest monitoring using satellite data. So, Matt, the floor is yours.
Thanks a lot, Henrik. Thanks to the network team as well for organizing this, and thanks to all the attendees. It's really neat to see the greetings coming across from all around the world on our shared interests on forest health. And I will be talking really about remote sensing, large-scale monitoring, how we do it, how we try to present our results in a defensible manner so that they can be used for policy and decision-making, and just go through a number of examples. And if I run out of time, I'll just stop. Our workbench is the satellite record, and Landsat is this virtual time machine that goes back to 1971, 72, and we have it still operating now. It has been a global asset. In other words, it's been acquiring globally since 1999 with Landsat 7, and it was made freely available in 2008. And now we have ESA's Copernicus program. We had before that Brazil with the CBERS, even though CBERS was not globally acquired, but the idea that progressive data policies, sharing the data as a piece of infrastructure that we can all look at and use to solve problems. And so you get the data and it looks like this. It's not usable. So our first, in my history working, it's all about pre-processing the data to a point where you can see the landscape and you can apply algorithms that will help you to bring out, to identify the contrast you see in the image, which would be forest, non-forest, forest clearing, stable forest. And we go through this process. And in our lab, which is the Global Land Analysis and Discovery Lab in the Department of Geographical Sciences at the University of Maryland, we have the entire Landsat archive in our processing. And Peter Potapov has built this automated system for, we take each image, we look at each pixel and flag whether it's a usable land observation or not. We compare that with a MODIS reference of surface reflectance, and we do a relative normalization. We take out BRDF or anisotropy effects from the data. And then we composite to 16 days, and then we have time series. And those time series can be used to map forest extent and change. And so we turn that kind of checkerboard mosaic of uncorrected, unprocessed data into something seamless like this, and we can make maps with this. And because these data exist as time series, we can track changes. We have these data available. The 16-day data are available with tools to produce some features and to apply our decision tree algorithms at this website. So the paper that Peter wrote is also like a theoretical basis document for the process, and we welcome you to do that. You have to download a lot of data. Obviously, it's not in the cloud yet. But we learn a lot about the archive and what's capable. We know that the Landsat archive, this is a challenge for doing any forest monitoring. How consistent is the record over time? The Landsat record is not consistent. 2012, we only have Landsat 7, which is impaired with a scanline malfunction. And so we have fewer images and of poor quality in 2012. And this poses a challenge for consistent monitoring. We do per pixel quality assessments on each observation. We do process systematically a normalization, set of normalization procedures. So this is not important to know the details, but just this idea that we're intimate with the data, and we try to make it come to a level, again, where it's user-friendly for large area mapping. In the end, we can compare our Landsat composite time series data with MODIS, superficially just see that we have what we would call top of canopy relatively normalized reflectances that are very similar to MODIS. And so we're off to the races. We can do mapping. And when we look at the time series and we want to see what we're looking for in terms of signal, we can look at, like in figure A, that's stable NDVI for evergreen humid tropical rainforest. D is a logging event in the boreal forest. You only see observations in the growing season, the winter. There's a low sun angle, so we have gaps, and there's also snow and ice, and so we don't get that, but we get the middle of the growing season. That's D. E, we have a clearing for a smallholder agriculture system in the Congo, and you can see that there's a clearing, and then there's a little intermediate period where the field is used, and then it regrows. And then F, we have a lower latitude forestry application where there's clearing, and you see the regrowth signal. So a lot of the thing with the time series is getting the net story, and we don't get the net story at high latitudes, not yet, because regrowth is so slow. So we're trying to measure both loss and gain, attribute what kind of dynamics are the causes of the loss, and rates of recovery, et cetera. So our main product is the Global Forest Watch work that we do with World Resources Institute and funded by the government of Norway, where we track stable tree cover and loss, and we're adding gain in the coming year to get something that is closer to net dynamics. And the utility of these data are in looking at trends. Off the shelf, you can see, if you see really big signals, you can argue that there is a trend. The big signal here is in the arc of deforestation in Brazil, where they did, for a period of a number of years, slow deforestation from a peak in 2004, almost 30,000 square kilometers down to 4,000, and then backsliding in recent years. But the whole idea is to see where these trends, how are they going? And in the tropics, we see a lot of warm tones, meaning that increases in disturbance. I just want to highlight, because we're in this new domain where we have cloud computing, we have fancy algorithms, all this kind of stuff. And this is like the cookbook for us in terms of what you need to do to get good maps. And we start with domain expertise. Domain expertise means if you're doing mapping forest, you should know something about forest. You should definitely know something about their geographic distribution. You should know something about the pressures on them, what kind of dynamics you could expect to find in different environments. And so when you work with your algorithm in the inputs, those patterns are evident. In the outputs, when you turn it into a categorical or a continuous variable of tree cover, for example, you see those and they have some fidelity. Your first order validation is your expertise as a domain expert. That's it. There's no black box stuff from our perspective. We don't crowdsource training data, et cetera. You need to know remote sensing in image processing and the data preparation, and in creating features that help facilitate mapping. So you can take 16-day data and put them into a statistical derivative and look at, let's say, the change in SWIR, the 1.6 micron SWIR band over time. It's a great band for looking at forest disturbance. So you need to know that. Obviously, you have to be intimate with the algorithms, so you know how they work, you know their behaviors, you know their kind of how they change when you change a parameter. And this is hard for deep learning on the deep learning curve, neural nets in general. But we'll talk about a little bit about that. When you're mapping, you have to define your classes very explicitly with physiognomic structural thresholds. What is a forest? It's not just an intuitive thing you look out the window and see and call that a forest. And the most important thing, and takes up half our time now, is to look at reference data that are drawn in a probability sampling framework, and you assess those individually, and they can tell you your map accuracy, but they actually are the answer. So we make the map, and the map is a stratification. I'll get into that. And we throw samples within these strata. And from those samples, because we've looked at these data in isolation, we can statistically say the mean dynamic is this plus or minus some uncertainty. Pixel counts are not what you would submit to a policy international protocol, for example. So this is our kind of cycle for making maps. We have the feature space in the upper left. That's fun to work with. It's really fun to be creative on the feature space, because a lot of times you're looking for the silver bullet that'll do the hard work for you. We have training data, which we can sometimes borrow from, let's say, JEDI, but we still have to add to it manually because there'll be commission errors on heights over barren mountaintops and the like. So you have to do this troubleshooting. We are using mainly decision trees. We do have some deep learning applications that are working, but decision tree algorithms are a thing. We get a map output and we iterate mainly on the training data until we get a final map. All right. So this is a great job to have because in the last 20 years, the capability has just blown up. We can do the globe. We can run our global algorithms between a day or 2 days. We can iterate 30-meter global data in our lab. We don't work on the cloud. We have our own computing system, but it's just like, it's hard to conceive of that 10 years ago. And other people can use Google Earth Engine or AWS or what have you and do similar work. Very quick turnaround at scale. We have advanced algorithms, for example, deep learning. We have globally acquired, freely available data. And now we have globally acquired commercial data in the form of Planet. And we have other players in there that I'm not sure about the global aspirations, but Maxar and Airbus come to mind. But Planet really sets a standard for thinking about the Earth as a single unit and acquiring data with an unbiased tasking. So our historical data were big meteorological satellites or big pixel, large swath, daily sensors. When we take Landsat 7 and 8, we get we get much finer resolution, but we sacrifice our revisit rate to 8 days as opposed to daily. Commercial satellites are now in the constellation format with Planet, Sentinel 2A and B with higher cadence than Landsat, and adding C and D soon. We can use those in a virtual constellation and get down close to the commercial sector, at least in terms of temporal revisit. But we do have this box around the commercial sector, and that's always been a problem for me because if the environment is as important as it is, as we think it is, we would advocate very strongly to have this infrastructure also available for more people to look at and to solve problems, but we do have this commercial limit. But that's kind of like the suite of assets that we have available for global forest monitoring. And then we also have tools such as Google Earth Engine, where we can avail ourselves of the entire archive and algorithms to do mapping. So this is great. This has had a leveling effect so that more people can get in the game, and this is fantastic. The benefits are obvious. Again, if you have more people looking to solve a problem, there's a higher chance that that will be solved, and maybe that you have a different range of efficiencies in solving that problem. The downside really is more information. We have a lot of folks new to the domain, and they're making products, and I would say we have to be very careful about overstating our capabilities in terms of making maps of questionable utility. And I could list a number, but really if you want to map biomass from space with optical data, the optical data don't see wood density. So you have to really be careful how you produce that product and apply uncertainties to it, because you really kind of don't know. There is no field validation of wood density that fits a statistical framework. Same thing with crop yields. We had a paper on restoration that was saying that a lot of tropical savannas that are wetlands were restoration opportunities. So we have to be careful how we roll out this capability, I guess is what I'm saying. What this does, this proliferation of maps, really does put a greater emphasis on the validation and the kind of independent assessment of it. So as we're getting better at sharing products and sharing, how we make products, we have to really share our reference data. We have to share our framework for validation and all the data that we're used to verify or to estimate area. That's a big deal for us. This is our framework for monitoring land cover and land use. All the trees stuff is on the left, but we're interested in mapping the biophysical kind of traits of the forest, height, cover, and we can divide that into different, types, dense forest, open woodlands, etc. And then we're interested, as we go down this hierarchy, going from cover to use, and so we can set aside natural forests and look at forestry, look at shifting cultivation, other dynamics that are related to trees that are land use explicit. And then if there's changes, we want to assign. This is the thing of the network, and we haven't made a lot of progress. We checked one box here. We're going to check one box here at the end of the year, where we can identify what is the change factor for any pixel that experiences disturbance. Is it mechanical clearing? Was it fire? Was it disease? Was it logging? And if we can do that, the value of our data, it grows exponentially. So we have a new product where the GFW map is going to have fire labeled explicitly. So any forest mortality due to fire is going to be its own class. It's a big dynamic, especially in the boreal. And in the boreal, it's not land use, it's not human derived, human caused. So this is, and we'll keep going down this list. So I think about the way, just from the mapping perspective, we can map tree crown cover, tree height. Those two things can be used to define forest. We like this idea because, if you look at FEO definitions and country definitions, they vary, but this is a way to harmonize, at least from a structural standpoint, what a forest is. So we can take a country like Brazil and we can apply a 5-meter height threshold and then look at different canopy densities and kind of, disaggregate the forest asset. We can add on top of that forest type. So the high biomass, high biodiversity forests that have tall, differentiated canopies that are long-lived, those could be a category in themselves, a forest type. So we've always mapped forest type of leaf longevity, leaf morphology classes. And so those can be categorical layers that we can put on top of the structure. And of course, we look at the changes. So we can look at changes, gross dynamics of all tree cover across the country, the dynamics within the stable high conservation value forest. And this becomes, very useful for a lot of policy objectives like REDD+. And we can do this at scale. We can do this across the 3 largest tropical countries. We can do it across the tropics generally. But the thing here is that these graphs are pixel counts. And like I showed with the data richness issue, 2012 is not a great year to map hardly anything compared to 2013. 2013, we have Landsat 8. We double our image frequency. We have over 250,000 images globally per year that since 2013. So we're in a sweet spot. But before that, it gets a little noisy. There are just vagaries of data quality year to year due to climate. If there's an El Nino, that can pose problems for your algorithm. And we are always tweaking our algorithm. So what's the point? The point is we don't trust pixel counts. Whatever we do, whenever we make a report or publish a paper, the maps are cool. We start with the maps, but then we use those maps as strata to throw samples of, and collect reference data. And from those reference data, we make estimates of areas. So I'm going to go through a number of examples here where really the map is a point of departure, and the map has no statistical properties. It's almost always biased. It's always biased. When you do the samples, you see that you under or overestimated the value that you're interested in your mapping, and so the area is the primary result from this exercise. The map accuracy reflects how well your map captured that dynamic, and that in the statistics will be captured or reflected with estimates of low uncertainty. So the map is really important. I don't want to say that we use the map to target our themes of interest. And this is really important for a country. If you have 1% change in reality for a country's forest per year, and you throw a random sample, you're not going to have low uncertainty. You're not going to capture that change. But if you have a map that is very good, you'll have a lot of samples in your target class. That 1% land area will be estimated with low uncertainty. So the maps and the samples work synergistically. We did some prototyping on this idea back in, this is 2009, comparing random, systematic, and stratified using a satellite-based map to estimate forest loss in the Brazilian Amazon. And we showed that this map as a stratifier reduces your effort tenfold in the case of simple random compared to stratified. This is a big deal because, you know, we used to be very happy just making maps and doing some cursory validation, maybe even training cross-validation, fine. But now we know that the actual answer's coming from the samples, and we spend half our time on sample analysis. It's just blown up our workload. But again, we believe it's important, especially with the proliferation of capabilities. You have to go through the process to show, you know, your map making is good, and then also put out this statistically valid, unbiased, and known uncertainty estimate. Here's a further little subtlety that is very appropriate for forest change. Forests on an annual basis don't change a lot in terms of percentage. So you have a small area mapped as your dynamic. Let's just say it's loss. So you could have this big green stable forest area and then these two patches of loss. If you throw a sample just in the loss, you will get your commission errors, but your omission errors of change are way out in this big ocean of green, and you don't have a good way to capture them, and you need to. So one of the things we've done is iteratively looked at a way to add another stratum to capture likely false negatives. And this is really important. Again, when you're doing change, you got to have both your commission and omission errors. And so our strata don't match the map. There's something different. We have this buffer idea, and the buffer can change right now. And this is from the Congo. In the Congo, if we just add 1 pixel buffer, we pick up 96% of our omission errors, our false negatives. So you throw samples out in the ocean of, you know, stable forest. You throw samples inside the loss and in this buffer, and you've covered it. Now, going back to the pixel counts of the tropical forest trends, this is what it looks like when you do sample-based analysis. And this is what we would say the actual numbers are, not the pixel counts that I showed before. So now we have annual estimates with plus or minus uncertainty derived from samples that are interrogated individually and then aggregated up to provide this time series. This is the answer, not the map. Going through another example from Central Africa, where we're adding value to the samples. So this I like this a lot. And you could, if you think about tree mortality from drought or disease versus wind throw versus logging, this is how you do it. You can start with a map of forest loss, and this is for Central Africa. Here is, you know, the loss highlighted over a decade plus. We can create from this a stratification. These are pretty ugly slides, I apologize. But this is our mapped loss, our buffered loss, and our stable tree cover from the map perspective. And so again, we're targeting the red and the yellow in a bias way. We're really throwing more effort into there because we want to find loss and we want to have samples that are on loss so that we get low uncertainties. And in the end, when we do this, exercises from Sasha Tukayvina in our lab, we can get very precise estimates of dynamics. Now, the key thing I want to add to this is that we're not just mapping loss, or we're not just estimating loss. When we look at a sample, we are saying, what was the pre-existing forest type? When was it cleared, and what was the land use outcome? So we don't map any of those things, but we estimate them through the samples. And this is a shortcut way, I think, to get at mortality rates and that sort of thing, where you could try to make a decent map of likely mortality areas and have a stratification around that. And that's when I talk about, Sasha also is making the forest loss due to fire map. That becomes a stratum, and it just makes our targeting that much better for these different dynamics. So here is a picture of, half of, 40% of the disturbance in DRC is primary forest, 40% of it's secondary forest. That's the shifting cultivation dynamic. Then we can look at the land use outcome. Over 90% of forest disturbance in DRC is smallholder ag. That is, the population on their own, without, in a largely stateless place, feeding themselves through shifting cultivation. There are no cheap food imports. There's no food aid. They're just feeding themselves. And they're clearing as much forest now with axes as Indonesia does per year with big machines. If we go towards the coast of Gulf of Guinea, you see the magenta purple color. That is selective logging. That's the dominant, or at least equal to smallholder ag in terms of area. That is a big money maker for foreign currency in Gabon and Republic of Congo. And then when we get to the coast, you see these blue colors, and that is big agro industry like palm. And so you're close to the ports. That's where that stuff is going. And some of it's coming in farther interior, even the Republic of Congo in the north. There's palm now. And there has been, but you can see kind of this gradation as you go from the coast over to DRC. Very different stories, but again, your point of departure is just loss. And from the samples, you interpret these dynamics. Then we can look at trends as well. We can also do this at any subunit. So this is work with the World Bank in Mayendombe province, and to set up a reference baseline emission level. And here you have a map of not just loss, but we're interested in emissions. So we have classes associated with emissions. So we're interested in primary forest loss versus secondary forest loss, permanent conversion versus repeated loss and gain. And we throw a sample, and you see the colors. The colors point to the west and the southwest in terms of their variety. That's where the action is in terms of change. So again, this map is telling us where to look, and we can look at a sample. We can say, here's the graph over 15 years. It was primary forest. It was cleared. The SWIR goes up. The red reflectance goes up. And we have a clear signal. We can tag the year of the event, and we can confirm an end state with Google Earth. But this is half our work now, is what I'm saying, this type of stuff. Looking at time series graphs of different spectral measures, looking at thumbnails of landscape scale pattern, and then supplementing that where we can with very high resolution data. I'm not going to get into that or this, but the end story is to do emissions. And so cool. We get it from the samples, and the map is hugely important. I guess we'll go back to this. The map, again, every time we do this, we can compare our efficiencies with the map to what we would have had to do with random samples. And it can be 5 to 10, 2 to 5 to 10 times the reduced workload. And this is a big deal. So we did this with 2,000 samples, and we're pretty happy. There are places where we don't stratify, and we do have one of our students, Diana Parker, is doing a study in Indonesia for 30 years, where half the country was rainforest in 1990. Half of that rainforest is gone. So if you throw random samples across Indonesia over this 30-year period, a fourth of them are going to land on primary forest loss. So there are a lot of nuances to the design of your strata, and whether or not you're going to get gains out of stratification in certain cases or not. But that's really amazing. She has really good results just using 10,000 random samples. This is a new project with NASA where we're using Planet as our reference data, and this will be interesting. Obviously, 3-meter data is way finer, more detailed than 30-meter, our map. We also have near daily acquisitions with Planet. Its radiometry is a bit rough. The bands are not as well, not even close to as well calibrated as we're used to. And there's a constellation of sensors, so the sensors all perform differently. You can see huge difference in the quality of imagery sensor to sensor. On the PlanetScope older series that we're going to use for this, but this is just a year's worth of validation of our global map using Planet, and we're excited to see if if that is a clean way to augment our area estimation. I'll give you, I'm going to sound like a salesperson for Planet. Planet is super powerful in the concept of higher resolution, higher temporal cadence than what we have from the medium resolution public assets. So let me just give you a picture. I'm not going to show all the Planet data, but if you go anywhere around the world and you just grab, Planet, you will see how dense the time series is. And a lot of what we do, even with, obviously with any optical sensors, throw away data. And in the humid tropics, there's more than likely clouds or haze on any particular image. And Planet has so much data that you can throw a bunch of it away and still get a nice time series, even in cloudy areas. This is Landsat over a 2B log concession in Northern Republic of Congo. Here is what the logging road looks like. I have it in true color, so it's kind of rough. Here is our best image at the time of logging extraction. So you can see the little noisy things, but it's gonna be very hard to map this. This is our best, highest contrast picture of the logging. And this is what it looks like several months later when the logging skidder trails and the extraction sites have covered up with vegetation and there's shadows from remaining trees. It's gone. What you see left are the roads. And that's what we map with our global algorithm. We map just a handful of pixels off the roads. Everything is on the road. And this is great. I mean, we're mapping the landscape. We know where degradation is occurring. And sometimes you do get the, like in the Amazon with the cloud-free window, you do see a lot more degradation in Landsat than you would in a place like Republic of Congo, but it's a limiting factor. Here's Planet, and I just cherry picked some images before logging, when the road comes in, when the logging starts, and here's the money shot where you have high contrast coincident to the action of the loggers, and there you go. That's the footprint. And you collect many, many images before and after this to get this one. Doesn't mean Planet's always going to get this kind of shot, but I mean, all things being equal, if you're getting daily acquisitions versus every 8 days, forget about it. This is going to be so much more valuable in terms of characterizing degradation events. And this is what it looks like in Planet just a few months after that. So, so again, this obscuration of this ephemeral dynamic in the optical domain. And there it's gone, so you just see the roads. Again, that's what we're mapping with Landsat, and that's what that one image at the peak of extraction shows. Pretty cool, pretty cool, pretty cool. Costs money, so good luck. I'm shifting gears here. Again, this is reference data. There's a lot of promise for us to use this as reference data to get more precise area estimates. Mapping at scale is another story. We'll see how that works. Another product, a different kind of product, are alerts, and there are a lot of alert products out there now. And I just to emphasize that they are of a wholly different nature. In our conceptualization, they are meant to be conservative and high confidence flags for disturbance. And of course, we have commission error on alerts, but alerts are really not supposed to commit error, and they're not supposed to be used for area estimation at all. If you have a logging road and you get 10% of that logging road mapped in near real time, it's a success because it's meant to inform land managers, different agencies that are responsible for the resource. And so it has a different character altogether. So right now we're doing Landsat 7 and 8, 30 plus or minus 30 degrees. We're going to global in 2021. The idea is that with every new image, you compare it to history and you can, with some reasonable confidence, flag change. And so this is a logging road in Peru, in the Amazonian, Peruvian Amazon. And here you see, even with the alert, we see some extractions off to the sides of these roads, but that's what we're doing. And It's produced every day whenever we have new images every day. And if we have viable surface observations, we run the algorithm. And then Global Forest Watch compiles a weekly summary and updates the alerts on a weekly basis. And it's a hard thing to do because you're using one image to compare to history. And so that constrains your kind of ability to do really good mapping. We have rules for repeat detections so that we can go from like a provisional single detection flag to a confirmed flag based on multiple identifications of disturbance. This is our historical record for an example, and then we have these in these blues, the 2018 through May detections of fires and some clear cuts. And it's pretty messy and noisy, but again, it's not supposed to be perfect. It's supposed to be something's happening here. That's the objective of this. And we are, it's cool because we are populating both now with Landsat and Sentinel-2, like the latest look of any of the geographies that we're monitoring. And so you have an image of, what is the most recent look from space? That's kind of an interesting perspective. Sentinel-2 is great in this mode. We see a lot more change. I'll just click through this. You'll see that the red here is Sentinel-2 only. The blues are Landsat only, and the white is both. I mean, Sentinel-2 just much higher detection rate. Not that Landsat is useless there, but it's greater to have more confirmed change and actually see the pattern as opposed to just a few blips out in the forest. So this is cool. Sentinel-2 is harder from the QA perspective because of not having the thermal band, especially in the tropics, but the 10 meter obviously has a huge value added. And we work with HEVOS and Greenpeace in a project in the Amazon basin to get these data out through Global Forest Watch, and Global Forest Watch has some other tools that to help use them in the field, like the Global Forest Watcher app that takes advantages of the alerts. Now I'll talk about some, I think, more data integration approaches. This is a new capability from space on the International Space Station. The PIs are off to buy in our department. It's a spaceborne LiDAR called JEDI. And with this, it's like the holy grail for us for calibrating Landsat data physically. We've done work with GLASS, the previous version of ISAT, and prototyped a number of, wrote some papers on prototyping the calibration of Landsat into heights from LiDAR shots. And now we've done it. Peter Popoff has published a paper in RSE. It's online now. It doesn't have dates or anything, but the proof is online. And this is from that. So we've taken through a certain time period, all of the JEDI data. We're interested in filtering by growing season. We want to have the peak canopy cover for that signal to be consistent in mapping structure across the planet. There's a lot of QA filtering on the JEDI shot side. And so, but in the end, you have hundreds of millions of shots. We compare JEDI to ALS to try and get what variable from JEDI we want to calibrate the Landsat by, and we pick the RH relative height 95 metric, and that becomes our training data. And we create a map of heights at 30 meters. And this is great because it's going to be really serve a lot of purposes. If we do time series of height, we're going to harmonize that with our disturbance mapping, and we're going to use this to do gains in tree cover. So it'll be the kind of like the base for getting both our gross and net dynamics in harmony, which we don't now. We just map loss. Excuse me. One of the things really important is that Landsat doesn't do heights over like 25 meters, really. We can in particular geographies get heights that are 40 meters, but in general there is no signal. The forest, once it gets dark and you have light extinction, and it can only get so green, it can only get so dark, and it's over. You cannot go beyond that. We also have trouble at the low end. That's more on the LiDAR side. These spaceborne LiDARs are not great below 3 meters. And we're trying with ISAT-2 to calibrate as well. We need ISAT-2 to do the to do the polar regions or the regions outside of the ISS orbit. Anyway, there's a lot of work to be done, but Landsat will not fit the bill for a lot of ecological applications. We're using it to track dynamics, and I think it's going to be really good. And this is an example of that, where you see loss and gains using JEDI calibrated Landsat time series. And from the left, you see loss dynamics in Brazil, and on the right, forestry and a lot of gain dynamics in Uruguay. How am I doing? Let's see. Okay, I got to get going. So our end goal is to use the biomass shots of JEDI and to build carbon stock strata. And this is a paper from Sasha Tukavina, where we created carbon stock strata across the tropics, and then put our loss on top of those strata, and through samples, so this is like the unified field theory idea, and interrogated those samples and had both from the LiDAR, these were glass shots from Alessandro Bacchini, were converted to biomass. We treat them as inventories over these strata and we calculate the mean carbon stock. We get the area from our traditional method of mapping disturbance and taking samples. And so we have sample-based emissions factors, sample-based areas, plus or minus. We combine those and we can get gross above ground carbon dynamics using good practices, using the appropriate sample-based things. So I'm super cool with that. And you can make some graphics that kind of fit that. I'm going to try and wrap this up. I'm going to give a nod to, this one other slide. We recommend highly, and we are getting into moving beyond just forest, but looking at all land cover land use dynamics as a whole. So on the left, this is looking at all the pressures, land uses that are encroaching on natural stable land cover, such as croplands, plantations, and pastures. In the middle, it's soybean explicitly as a pressure on the rainforest, and we see that it's not. The soybean generally replaces pasture. It's really the cattle ranching that is the main driver of forest clearing, especially with Brazil with the policies of the early 2000s. And when we look at fires, you see that fire is all along the periphery and the edge of the Amazon. It's far away from cropland, and the idea there is that when the press gets stories out on soybean as a cause of the fires, it's not. But the point is, when you combine all these layers together, you get the whole story, as opposed to looking at the forest in isolation. That's the whole point of this slide. Okay, and I just want to give a nod to Jim Tucker, who's a colleague from NASA Goddard, published a new paper where they're mapping trees individually using sub-meter commercial data across the Sahel, and crazy amount of data processing, a lot of inconsistent data. But this is moving to the next level with deep learning to identify individual tree crowns where a tree is defined as a 3-meter diameter object, and they can map 1.8 billion trees. I think you still have to do, regional validation of some sort, but this is kind of the next level stuff, where if we do get into the commercial domain and our images are beyond the object of interest, wow, now deep learning is fully super appropriate. And the question is, as a proof of concept, where do you go from here if you want to try and monitor this kind of thing? But the first thing Jim's doing is extending it across the Sahel. So I got some comments there. I don't really want to get into them too much, but so I think I'm done. And I thank you all for your patience and your time listening.
So thank you very much, Matt. This was very impressive. It's a lot of information that needs to be digested. So we were planning actually of giving us 5 minutes to collect the questions and then start the question and answer period. Is that fine with you? Do you have enough time still to hang on for it?
Sure.
We're sort of getting ready, and people are still hanging on, so they're keen to see what your responses to the questions. Cornelius, you want to start?
Yeah, I think Matt can choose the question himself, and he's picked it already.
It's too many. It's like it could be a couple courses given on this, I imagine, or a semester's worth, because there's a lot of nuance. The one question was very interesting, where fundamental was, why don't we trust the pixels? And when you're running an algorithm, and you can imagine if you're mapping big soy or pasture clearing in the Brazilian frontier, the changes are huge in area. They're deforestation, the trees don't come back. And so you have so much signal that when we compare pixel counts to our sample estimates, they're very close. You could argue that, you could just count pixels. If you go over to Central Africa and the fields are less than a hectare and most of the pixels that have disturbance are mixed pixels, getting a consistent algorithm application to really nail that is very hard. So it really has to do with how unambiguous the target class is, how extensive it is in area, and the samples, the sample-based estimates start to look like the pixel count. Further complicating it is really the inconsistency of the Landsat record. We need to have continuity so that algorithms behave predictably year to year to year to year. And when we go from Landsat 5 and 7, which are whisk broom scanners, they have less signal to noise in terms of their performance, to Landsat 8, which is push broom, and the sensor, the dwell time over land parcels is much greater, and it's just better engineering. Wow, we have 15 times signal to noise. You're not going to map the same thing, just like that. And so you have this problem. If your algorithm, I mean, typically when we version, we want to run the algorithm over the whole thing, but sometimes we do it in real time. We tweak something, and then that could be a little bit of an offset. So in general, getting the pixels to be trustworthy is a big challenge. And by doing the sample-based estimate, you're looking in isolation at a particular place with an expert, and we do have teams. We'll have, like, say, 2 experts looking at a sample. And then if there's a disagreement, a 3rd expert will come together and there'll be a consensus filtering. But in the end, you're like, the algorithm has to extrapolate over all this area, do all this stuff perfectly. When you're looking at this one thing in isolation, you're like, I know what happened, and you label it. That is so far our most defensible way to report areas. And it really has to do with the statistical properties of the method. Again, the map as a pixel count, you don't know its uncertainty, you don't know, its area, unless you do something like a probability-based sample. So it's just kind of fundamental now. I hope that's sort of clear.
A couple of questions were on other data, like radar data. Can you maybe give a little bit of input on your opinion on radar data?
Yeah, radar, the Sentinel-1 is the first of its kind in terms of, being free and openly available and off the shelf, pretty much, usable. We have played around with it in crop mapping. We haven't incorporated into our alerts or annual updates. I think for alerts, it's got to be great, because in some of these, a lot of clearing is timed with local dry season. So, but there are behaviors, especially in the Amazon, where logging is going on in the rainy season, and I'm sure we're missing that, and radar will pick that up. So I think in terms of reducing overall latency of alerts, radar would be great to add. And to the degree to which it would in a time series also augment the longer time annual updates. I'm sure it would add something. It always does. But we haven't the bandwidth, really, the resources to do it. We have aspirations to.
Another topic that's popping up quite often is, what's the minimum scale of disturbance you can map? So is it only stand replacing, or is it also kind of non-stand replacing disturbances? I guess you hear this question quite often, right?
Yeah. Well, it has to do with the quality of the imagery. I think the example from Planet really spells it out very clearly. If you have an image, because a lot of degradations, when you're talking about fine scale sub-pixel or pixel scale changes in isolation, they could be ephemeral in the signal. And so it's really about when that image was acquired. Did you get it in proximity to the disturbance? And then you have a signal. If you don't, you will omit. And so you could have the same dynamic and capture most of it or omit all of it. So it's really not a question of what's the finest you can get at. And I don't really know the answer to that. But for sure, because we've done field work in the Republic of Congo, when they take out a big tree and it falls over and there's slash and all this kind of stuff, if the image is at the right time, we will see that one tree removal, even with Landsat. There's a bright contrast. So it really has to do, it's kind of disappointing. I think most of the land cover land use user community, they want time domain improvements for agriculture, for forest monitoring. And I think that, institutions like NASA don't think more of the same is exciting technology. They'd rather have more bands or some other signal. And we just want more temporal density. And the temporal density is to capture phenologies and natural dynamics, but it's also to overcome atmosphere. So I think that it's not, I don't know the answer to that question specifically, but we get to it when we have something like daily high res, like Planet. Conceptually, we can start looking to answer that question. And just furthermore, depending on your observational scale, you have cryptic change that you just cannot algorithmically consistently capture. So if your pixel's 250 meter, 30 meter, 10 meter, 3 meter, there's some fractional removal that an algorithm cannot consistently capture. So it's all scale dependent, obviously.
Okay, another topic popping up quite often is distinguishing between different types of disturbances, kind of distinguishing between loss or permanent loss and harvest, or even insect or wind disturbances. Any comment on that?
Right. I mean, there are signals that allow us, the backdrop to this slide is Sasha Tukavina's to be released differentiation of our disturbance mapped into fire versus non-fire. I mean, fires have a very characteristic spectral signature, and so we can target that, and you could target per pixel or deep learning, whatever. I think it's a pretty tractable problem. Storm damage is really hard because storms, they do have this shape, this kind of path that they cover. But one of the tricks with wind throw is in the satellite, a lot of times it might just be a defoliation event and it comes back. So I think storms, tornado tracks, hurricane landfalls, derechos, I mean, what a cool thing. We see them in the image. We know where they are. I think that's definitely a deep learning thing. And if you can kind of build a taxonomy of the shapes, you probably could do it. The disease stuff is interesting because some diseases, and I'm not the ecologist, but if you have gypsy moth, it could be a very strong signal, but it didn't kill the forest. So the idea of tuning your algorithm for the mortality and not the ephemeral is really important, and whether that's a slow or abrupt stressor that leads to mortality poses problems. But we do pick up all the landscapes that have, for example, mountain pine bark beetle deaths, from South Dakota to Colorado to British Columbia. We see that. We see other vectors in European Russia. And so again, it's analogous to the storm thing. What are the spatial patterns? What are the characteristic shapes and spectral signals with that, and just try to train it. I think it's super. I mean, people should investigate that because again, we're checking the box, but slowly. I think one of the challenges for us as a unit is in this operational mode, we have to keep, we're still making these products and we're adding products, but we also have to be doing research, right? So if you're free to just dive into the research and look at some of the stuff, have at it, man. There's plenty of opportunity.
Okay. Any other question that you think is interesting to answer?
Well, let's see. A lot of people talk about land use planning and the like, and I mean, of course, satellite products help you understand remaining natural vegetation types, the idea of restoration and building corridors. I would like to see more spatially explicit, land use planning projects incorporate satellite data, and restoration is really one of those where the commitments are so huge, but there's no geospatial data behind them. Where are the commitments? We're looking at the satellite for regrowth in countries that have really big, million hectare commitments, and we don't see it yet. So I think I like the idea of scenario modeling and also land use planning as a framework for intent and additionality. So we need that. That's this idea of transparency. What transparently are your ambitions to restore or plan or whatever? And that's just so lacking generically. So there were a couple questions on that. Natural forests versus plantations. The plantation signal is the cycle, and we can map where trees are coming and going at low latitudes pretty easily. And trees are coming and going in forestry, formal forestry, lands, and also shifting cultivation. And we can differentiate those based on kind of like the scale and some of the spectral characteristics of the time series. They're different. So there is a way, absolutely, to do that. The forestry at higher latitudes is trickier because we don't typically see in a lot of places the regrowth in the time series. So, you might have to use shape or, a deep learning kind of approach to say that shape indicates forestry. And then, you really want to separate out, where Canada calls everything forestry land use, but they are clear cutting old growth forests. And so you really would, I think, from a carbon perspective and from a habitat perspective, differentiate what is called forestry in one place would be called deforestation in another place. So you try to pay attention to that as well.
Someone asked about the forest product you mentioned coming up. Can you give a bit more details on that? Which product? The forest fire product.
Right. So it is in this hierarchy of loss. We want to separate out mechanical removals, and those could be differentiated in two ways. One would be scale, like clear cuts versus noisy looking degradation events, but they could be both called, clear cut logging kind of discrimination. And then everything else would consist of, what we talked about already: fire, wind throw, disease, and then other natural dynamics like river meanders, landslides, and the like. And I mean, again, from a research perspective, I can see strategies for mapping each one. In this case, and in that other, in the general framework, if we map loss well enough, then we just go back to those pixels and analyze those pixels in isolation and attribute them to a driver or approximate driver, a change factor. So this backdrop image, you can see in the top right, this is Russia, where, and you see this also in Quebec on the top left, where logging is co-located with fire. And so you have an algorithm that is trained on the different signals, and they're very different, of the mechanical removal versus the fire. And you run it and say, all of the red is fire. In the tropics, it's a bit trickier because there's a lot of fire after clearing. So we're talking only about fires in standing forests. So in the bottom left in Xingu, you can see the fires along the Xingu River from smallholder ag, escaped fires. And so that is fire that doesn't have anything to do with a chainsaw clearing it initially. Same thing in Indonesia. In both those places, when they make a big clearing, the biomass is piled up and burned. But that's not what we're talking about. We're talking about fires in standing forest that led to mortality, and using an algorithm to say that's what happened there. And then when you talk about the human attribution at low latitudes in the tropics, these are human induced. And then we get very controversial, where in the temperate to the boreal are the fires human induced versus the natural dynamic? And that I cannot solve. We could talk about that, but that attribution of the cause, the agent, is somewhere controversial. But at low latitudes, largely human induced.
Okay, so a couple of questions regarding the planet data. So first of all, I mean, the planet data was made available through the NICFI, and people ask, what's kind of your opinion on this? And secondly, whether kind of planet data will in the long term replace Landsat as base data for the forest loss maps?
You know, I think such a good question. I mean, I think when you go down to 10 meter and you have this constant, you know, Landsat has aspirations to match Sentinel-2 in future missions. And once you have a constellation of that kind of capability, 3, 4, 5 sensors, Planet with its current quality of data couldn't match that. I would go straight with the better calibration, the SWIR bands, all that kind of, that would probably be my preference. With Planet, the historic Planet, they're going to try the details of adding a SWIR band and improving things. I mean, I'm sure they're always improving. But the archive that you have right now is a tough one to work with. And it's because it's only visible in near infrared and not as well, you know, not as well calibrated, the spectral response. So I think Planet has still some work to do, but it's a fantastic model in terms of this iterating quality all the time, and they have just monotonically improved their quality. So who knows where they will be in a few years. The NICFI product is a monthly mosaic, and I've only read on the website that they use blending, and you can imagine blending across scene boundaries. That's not something that we would do from a compositing using radiometric corrections and rules for compositing. So, and the haze that's in there, we'll see. I mean, it's awesome to have that asset to test it. When I look at it, I almost feel like I'd like to go back to the individual data and create my own composite. But that's obviously a ton of time. It's an insane amount of work for even a small country. So I don't know. I don't have a good response for the NICFI data at this early stage. We'll see what comes of it. I think just time will tell. I can't judge it right yet.
Okay, one last very quick question. What about Sentinel-2? Will it be included as a data stream, kind of in the virtual constellation, or will you stick to Landsat?
Well, we're already starting to put Sentinel-2 into our alerts, and we use it in crop applications. The red edge bands are awesome for crop discrimination. So what we need to do is really get into the kind of daily download thing. So our unique position is we are downloading all the Landsat, and we'd like to do the same thing with Sentinel-2, but they put a lot of speed bumps in. We're trying to figure out, well, how would we, if we wanted to do even pan-tropical near real-time monitoring, how do we get Sentinel-2 in our lab to do that? So our main thing are logistics, and they're pretty daunting. Our aspiration is to grow Sentinel-2 because those instruments are awesome, and the bands are really, really valuable for certain applications. Missing the thermal is a big deal, but it's okay. Yeah.
Okay, cool. We got many more questions. It's over 50, over 60 in total, but we ran out of time. But I hope we kind of could answer at least some of those. Thank you, Matt. And I hand over to Henrik again.
Yeah. Well, thanks, Matt. This was really a great presentation, and you addressed all these questions very nicely. I may have one additional final question that where I'm particularly interested. Given your experience with the developments during the last decades, let's say, in the techniques, in the how the resolution improves and the spatial coverage and so on, and the frequency of the data availability and so on. So what do you expect? Like, when could we count on getting information in individual tree mortality?
Yeah, well, that's why I really wanted to show Jim's work in the Sahel, where you can't see that with the big pixels at all. I mean, that detail where you go beyond the object, and the objects are well behaved. In other words, they're separated by space. It's a wonderful experiment where you can make it work. And then as they get grouped together, I mean, there's been a lot in the literature, just a ton of tree identification projects. So it does seem like we're absolutely scale dependent. It is in the commercial domain when you want to get to that level. I would say that it is, you know, for the, you know, Digital Globe back in the day, they got $800,000 a year for their budget from the government, mainly defense contracts. So they really didn't, you know, I mean, their commercial side, I think, was not a majority of their business. And I'm curious about Planet and other, you know, and Maxar and their business model. And if there is going to be a very strong argument to maintain that kind of box around the private industry, when, you know, at the same time can make arguments that there are critical global environmental issues that would benefit from systematic monitoring for applications like you're talking about. So there's a big discussion in the political side for us to crack that threshold of 10 meters and get down to what you're talking about. So it's the capability is not really based on I don't think technical stuff. It's political and other considerations around, you know, industry and public good.
Okay. So thanks a lot. So it's money lacking in the end, which will.
I guess. I mean, well, it's not even that. I think it's like, well, you know, they've done studies for Landsat to show the value added of Landsat as a free piece of infrastructure, and it more than pays for itself. So the idea, it's money in a way, but it's also special versus public, right? It's particular interest versus public good. That's really what it is. The money, the benefit is quantifiable as a piece of infrastructure, because the value added of all the applications pays for it. And then, you know, the good out of that is that we solve a lot of problems a lot more quickly.
Good. So this was a very nice closing remark. I think we thank you really very much for having this seminar for us. I think this was highly attractive. We had in the end almost 400 participants, and I think this was a very nice kickoff meeting. And we hope to see you during the next advisory board meeting then again. So thank you very much. We can't see the attendees and we cannot hear their hands clapping, but I'm pretty sure that they all do, and I do this in guise of for the all attendees. So thank you very much.
I mean, really lovely. I really think it's great. The people from all around the world. This is a cool thing. We didn't do this before, and it's really
no, we can do it, and we don't have to fly around and even some more
participation is great.
Yeah. So thank you very much, and thanks all to all the attendees. This was a great meeting, and stay tuned. There's going to be more of that very soon. So have a nice day.
Bye.
Goodbye, everyone.
Bye. Thanks, Matt.
Thanks. Thank you.
Bye, Matt.